Nizar Touzi. He is a professor at New York University. He's currently the chair of the Department of Finance and Risk Engineering at the Tandon School of Engineering. He was previously professor at the Department of Applied Mathematics in École Polytechnique up until 2023. His contributions to mathematical finance, I don't think we need to go over all of them here, but they're quite wide and deep, also into applied probability and control theory. We all know that he's contributed immensely to this field. His accolades includes being the Paris Europlace Prize winner of the best young researcher back in 2007 when he was a little kid. And he was an invited speaker at the International Congress of Mathematicians, receiver of the Louis Bachelet Natisse Prize of the French Academy of Sciences, and was awarded an advanced ERC grant. Please join me in welcoming Nizar Touzi to tell us all about Martingale model risk.
Everything is turned on, it's all good. I just need to put it in your pocket and this one just put it on your
Thank you, Sebastian. Sorry for the long introduction. When you get those long introductions, that reminds you that you have been within the community for a long time, right? So people have more to say about you. Anyway, so very happy to be here. Very happy to see all the friends. I cannot do otherwise but remembering my friend Tom Hurd. I met him, he invited me very often to this place, and he's missing me a lot. We have the same birthday, Tom and I. And as he used to say, we have the same birthday as Margaret Thatcher, which from his says was not very like a regret, but that's life. Okay, so I will be talking about model risk, and this is a subject I have been interested in actually 2 or 3 years ago, and I was brought to that by a beautiful talk from Jan Obloy. So I will explain what Jan was explaining and show you what we have introduced around that problem. This is a joint work with Nathan Sol-Dubois, PhD student, my last PhD student in Paris. He's still in Paris, finishing his PhD this year. And so I will be talking about how to address model risk. So, okay. So let's start. What is a model? First question is, what is a model? A model is, first we teach us that any model is wrong, because the model is a representation, is a simple representation of the reality. And it has to be simple, otherwise you cannot use it. Then it's wrong, but it has to be smart. Modeling is not an easy task. So you see in this picture, everybody recognizes the person behind the picture, but it's just a few lines. You don't need many details in order to see whose picture is this. And so for us, random modeling, I would summarize a model by 2 items. First, the choice of a probability measure on some underlying space, which hosts the phenomenon that we are interested in. So typically in this talk is going to be finite dimensional, RD. But it can be the path space, it can be more involved than that. So a probability measure, and then some criterion. Criterion could be an optimization criterion or control in dynamic model, but could be more involved, could be an equilibrium, which results in some function at the end, the criterion that you are interested in. So throughout this talk, I will be introducing a probability measure, and then some function of this probability measure that we are interested in. And the question of interest is, once you fix a model and this model is wrong, in this picture, visually you can see that the model is not so bad. It's very simple, but visually you can see it's not so bad. How to measure that it's not so bad? How to measure model risk? Of course, a very old question in many fields, not only in finance. Okay, so traditionally, this question is addressed by sensitivity analysis. And in finance, in particular, I will focus on finance. In finance, in particular, let me take the example of European options pricing. European option pricing, in this case, you have probability measure mu, which is, as you know, the so-called risk neutral measure. And then you have an option price, G. G is an option price. Simplest example. And then evaluation function is just a linear function of mu then. It's the integral of G d mu. It's the simplest example, linear function of mu. So we have to choose a probability measure mu. Underlying space here is simply RD. And at some point in my talk, it will be just R2, because they will have two stepping types. So dynamics will be very poor, but already you will see that there are some interesting problems there. So think of any models you know in finance, starting from Black-Scholes. Black-Scholes is exponential of a Gaussian. For this Gaussian, you need a mean and a variance. These are the parameters. And then you compute the so-called sensitivities, or in finance, they're called Greeks. Then you compute the derivatives of this price with respect to parameters. Of course, everybody knows that. So the distribution is taken within a finite dimensional family of laws, of probability laws, mu theta. So the question is what to take for theta, what numbers to put for theta. Well, calibration, statistical estimation. Nowadays we say learning. We don't say estimation anymore. And then, okay, you decide to put some value theta. And then how do you know that value is good? You never know. And then the risk management team computes sensitivities. Sensitivities are, you differentiate now this value, the resulting value, with respect to parameters. And as long as these sensitivities are large, you don't sleep well, because this means that whenever the model moves a little bit, if you do a little mistake on the model, then it costs you a lot. So the job of the risk management is to make sure these sensitivities are as small as possible. And that is typically done by using other instruments in finance. So typically, in the risk management, practitioners introduce zero-cost instruments so that they can reduce the sensitivity. In the idealized Black-Scholes model, you can actually kill the sensitivity with respect to the initial stock price. But with respect to the other parameters, you cannot do it. But so, for example, with respect to volatility, people typically use other options to hedge a given option or whatever. So they introduce other instruments. So I will go back to this. This is going to be central in my talk, the hedging part. So we're going to introduce the hedging. Okay, so sensitivity analysis, widely used, not only in finance, by the way, any engineering, any model, there are parameters, and you have to fix these parameters, and you have to make sure that if you are a small error does not induce big mistakes. So in finance, typically this theta parameter in these models is about 5 parameters, but at the level of a trading floor or at the level of a financial institution, they would have models for several assets. So variance, covariances, also models for yield curve or yield curves, multiple yield curves, models for exchange rates. So it's typical that the dimensionality of theta is very high. Very high means I was saying 150, and one of my friends practitioners said 1,000. So in these models, they do have 1,000 parameters. And then when you see that, how do you manage to keep 1,000 sensitivities? So we are running in a space of 1,000 dimensions. The gradient is 1,000 components. how do you succeed to follow all these 1000 sensitivities and make sure they are all small? Well, this is the job of practitioners. They have many recipes to do that, but I believe you can do better. One way to go better is to introduce this worst case deviation problem, robust optimization, so-called robust optimization, which is around since a very long time. So this is not new. Robust optimization is, now you may have 1000-dimensional parameter theta, but in fact, what you are interested in with this criterion is the worst deviation. What is the worst deviation? So take a small ball around your parameters, theta, with radius r, and then compute the worst evaluation around that ball. So this has many good features. First, instead of working on the space of 1000 parameters, now you are turning to a function of one variable. One variable is the radius of the ball. So in particular, you may compute sensitivity, but sensitivity now with respect to the radius of the ball. First order correction, why not? I think that's a good idea. This would tell you in this space of 100-dimensional directions, what is the sensitivity to the worst direction? This is what this criterion would be saying. Now, if it happens that this function, there is no double bar g, that should be a g. If this function is concave, then you may also do convex duality. This has been done in several papers, many papers in operation research. There's a huge literature on this. Convex duality, you can always learn something, or at least helps for numerics. And in that case, F0 is concave, and you know that sensitivity exists. Sensitivity exists at 0. And you can probably compute that. And you may also go to expansion to higher order. You may not stop at the first order. You can go further if the regularity is there. But still, although we are considering, we are back to the one variable function, so only one dimension, behind the scene, we are only considering deviations within the finite dimensional family of models. So if we start from Black-Scholes, we are just saying what happens if the mean is wrong, what happens if the variance is wrong. But we're not saying what happens if the tails are a little bit thicker. We're not saying anything about what happens if there is a jump component, even very small, which keeps us in the ball. And for that reason, people have been introducing deviations in the set of measures. So instead of taking this ball around the parameters, we would like to take deviations around the law, around the Gaussian random variable. And then the question is, which norm are you going to choose? In which sense? In which sense? First, a good thing about that, in this particular example, is that you don't need this map to be concave. Now we're going to be talking about the map mu associates integral of GD mu. In this particular case, it's just linear. So it makes the math easier. We're going back to something which is, I mean, concavity in the parameter theta is a weird thing to ask for. The function g is part of the problem. That's the payoff. But now the fact that mu has some property which makes this map concave, it's exponential Gaussian. I don't know even if it. So it looks very weird to impose this type of conditions. While if you go to the measure space, this becomes linear. So you can say more things. There is a huge literature considering this problem with the entropy deviations. in OR. Many papers, many papers. I'm not citing any references here, but you can find many papers. But entropy deviation is not good for us, because if we think about continuous time models, this means that you don't have any freedom on the sigma parameter, on the volatility. Whenever you change the volatility, the models are singular to each other, entropy is plus infinity. And recently, deviations were considered in the Wasserstein sense, in the sense of Wasserstein metric. And this is what I'm going to focus on. And it turns out that with the Wasserstein metric, things are really nice. Okay, so let's go there. Now, this is my problem number one. I will start from here. So the worst deviation within a ball in the Wasserstein P distance, centered at the model mu that you choose. So mu is your model that you have chosen. You believe this model is not too bad, but you know it's wrong, right? And then you would like to know how wrong it is. Is it, right? Supremum, worst deviation of my criterion, again, a probability measure and a criterion G. Worst deviation within a ball of radius R. Okay, this is the Wasserstein metric, which computes the Wasserstein distance. I think people are more or less familiar with this by now. And I will be denoting x and x prime, the projection on coordinates. So these are couplings, and x is the first canonical projection, x prime is the second canonical projections. So these are joint measures on RD cross RD, where the first marginal, x, is distributed as a given measure mu, which is this mu here, and the second marginal on the second component of RD, this is x prime. X prime is the projection on this coordinate, has distribution mu prime. So these are the coupling measures, and this is the definition of the Wasserstein P distance. So in the last example, we were considering this linear evaluation function. Capital G is just a linear function of mu. Very beautiful paper of José Blanchet and Mercy, where they studied in details this problem. I think they are the first to have a systematic study in full generality. This paper looks like, for those who are familiar with optimal transport, looks like the Keller paper, where it considers the most general problem. And in this paper by Daniel, Samuel, Jan, and Johannes, this is where I got interested in this subject. They are considering an evaluation function which results from an optimization problem. So infimum of linear functions of mu, so that's a concave function of mu, with the A here, which is a compact subset, so concave Lipschitz, let's say. And I would be considering a general function G. That's not a big deal, in fact, considering general function G. Any questions so far? So this is the central object, robust evaluation. Instead of working directly on G of mu and trying to do sensitivities for G of mu, by the way, sensitivity for the function G of mu now in infinite dimension is an infinite dimensional gradient, right? So you certainly don't want to do that. And in this point of view, you take the robust point of view and you focus on the dependence on the radius. So it's a one variable function. And in this case, it's immediately concave. Because whenever, in this example at least, or if you assume that the capital G is a concave function of the measure. Because just the triangular inequality, concavity in R. So this is a result in the paper of Blanchet and Murthy, and actually parallel work of Esfahani and Kuhn is deriving the same result, but in less generality. I think these were parallel works, and these were the first to get interested in this Wasserstein ball in this specific problem. In this case, you can do the dual formulation, which is just you see. Remember, the problem is this supremum over the Wasserstein ball. So you write that this is a sup under the constraint that the Wasserstein distance is less than r, and then just penalize that constraint. By penalizing that constraint, the lambda is the Lagrange multiplier for that constraint, and just you keep working. Formally, it's a few lines. You can end up with this formula, but as usual, this is just the formal derivation. But at the end of the day, you have to justify the min max, the inversion of the min max, and this is where it gets more technical. And in this particular case, you see that the dual formulation is particularly easy because this function now is a linear function of mu here, and the phi lambda is just the finite dimensional optimization. If you move the y, this is an inf convolution somehow. If p equals 2 would be inf convolution of function g. So again, we reduce the worst case value function to a scalar optimization. And the standard question, if you want to kill this method, you say how to choose R. No clear answer. You may also ask the question how to choose P. No clear answer. And I will not have a clear answer about that. I will typically be choosing P equal 2 because it's more convenient for the calculation. And from this formulation, you can also think about, again, this is a concave function. Then what about sensitivity at 0? This is what was determined in this paper by Jan, and I think it's really a great idea. This is where I get catched by this problem. Well, it turns out that the sensitivity at 0 is given by this easy formula. So what they were doing this concave function of mu, where A minimization over a compact finite dimensional compact subset A of a linear function of mu. And the result is that the sensitivity at 0 so this is a small ball robust sensitivity, if you want, at r equals 0, is just another option price, almost up to the 1 over p prime here. So p prime is the conjugate number of p. If p equals 2, p prime is 2. And then it's about the gradient of this function g with respect to the x variable evaluated at the optimal control a hat 0 for the initial problem g of mu here, because there is a hat r would be the optimal control when you fix a radius r. So this is a notation. You fix this. You fix the a to the optimal control in the problem without deviation, and then raise it to the power p prime, LP prime norm, LP prime norm. That's another option price. So in principle, you can compute, if this is Black-Scholes model, you can compute the Black-Scholes evaluation, and in parallel, in the same Monte Carlo, you can compute this sensitivity. So it's very easy to implement. It's a very beautiful formula. This was obtained in the paper of, in this paper. And notice that it is not an immediate consequence of this. One may think, oh, once I have this formula for any r, it's concave, then I should be able to get it. Well, it's not so trivial. Typically, what you expect is that if you want the derivative at 0, then you would differentiate inside the inf and evaluate at the optimal lambda, right? That's the so-called envelope theorem, right? But if you do that, p is strictly greater than 1. Well, we need to have p strictly greater. There's a whole inequality somewhere. So p is strictly greater than 1. So if you do that, then you get p r to the p minus 1. But at 0, that goes to 0 again. So the lambda, the optimal lambda depends on R, of course. So it's about the limit of lambda of R times R to the p minus 1 when R goes to 0. And this result typically tells you this lambda of R has to go to infinity so that you have infinity times 0. So it's not obvious. So you really, if you want to reach this result from this method, then you need to understand what is this lambda of R doing in terms of R. And it's not obvious. So in this paper, the technique to do it is using optimal transport type of arguments. And again, this result is very appealing. You can compute it by Monte Carlo in parallel with the option price if you're interested in option pricing. But you can do it also in portfolio optimization. One of the examples they were considering, portfolio optimization. One-step portfolio optimization here. There are many extensions. In this paper, they have the first order correction for the optimizer A hat R. The optimizer A hat R is the optimizer for the F of R problem, robust optimization. And they also can deal with the case of finite number of linear constraints. So what happens if my measures mu not only are confined to be in a small ball, but the deviations have to respect these moment constraints. Again, Lagrange multipliers, but you have to justify that things work well. And this is done in these papers. But nothing is done for infinite number of moment constraints, which is interesting for us in finance, because if you want to do calibration, then you want to fix one marginal. Fixing one marginal is infinite number of constraints, moment constraints. And also typically in finance, you would like to prohibit arbitrage. So you would like to consider deviations which are consistent with no arbitrage theory. And for that, you need infinite number of constraints, of moment constraints. And this is what I would be interested in. So before going there, let me mention one more extension, which was in this paper by Daniel Bartel and Johannes Wiesel, where they extended the previous result to the dynamic case. So what happens if my function g depends on some process x at several times x1, x2, x3, finite number of steps. No continuous time so far. In this paper, no continuous time. So I'm writing it in 2 steps, x1, x2, two points in time, x1, x2. So exactly the same problem. Same problem, except that x now has 2 components, x1, x2, 2 components, each one in RD. So we're living in RD times RD. And oops, shouldn't get very close. And for this dynamic problem, what is highlighted in this paper is that, well, for these dynamic problems, we should be using the adapted Wasserstein distance. So notice the add here. So I'm adding this notation add to my initial function. Was my first function with the Wasserstein distance was just fp, only p. And I will keep adding other indices during this talk. So the first one is add. So adding the add, but add is not for adding, it's for adapted. It's just changing the ball from the Wasserstein ball to another ball, adapted Wasserstein ball, which I will remind you very quickly and give you the main intuition about that. And in that case, if you restrict to this adapted Wasserstein ball, then the sensitivity at 0 can also be computed. And it also has this very appealing and simple formula. Again, it's an LP prime norm, again, of the gradient of this function g evaluated at the optimal control without deviation, a hat 0, except that I'm adding this add again also on the gradient operator, gradient with respect to x add. And this notation means that the first part of the gradient is projected on the first component x1, condition expectation. This is a notation. Let's keep track of this notation. So exactly the same formula, except that the first part of the gradient, before taking this LP prime norm, is projected on x1. Okay, again, very simple formula. If you're doing Monte Carlo, this can be done simultaneously with your evaluation. It is done in finite discrete time, doesn't make any difficulty to extend it to n steps in time. And the main application that Johannes and Daniel had in mind is the application to optimal stopping, American options. There is a dual formulation like the Blanchet-Mercy dual formulation in this context, which is in an archive paper of Jan, who is a PhD student of Jan Obloy in Oxford. And recently, there is a continuous time extension of this point of view by Jan and his students. The paper is already on archive. Okay, so what is this adapted Wasserstein distance? Let me say 2 words about this. The adapted Wasserstein distance comes from this graph, which I copied from the paper of Matthias Beigelberg and Julio Baikov and Sigrid, 4 authors. Sigrid Kalbrad and who is the 4th? I don't remember, 4th author. Anyway, sorry to forget his name. So this is a picture, the easiest dynamic picture. 2 points in time again. You have time 1 and time 2. And of course, it's interesting because time 1 is already random. So you need to put 3 points in time, 2 periods. Period 0, 1, period 1, 2. So you see that in the first case, at time 0, you already know what's happening at time 1. So it's completely degenerate. So whenever to realize where you're going later, you need to wait until time 1. While in this graph, immediately when you get out from 0, you already know if you're going to end up at +1 or at -1 at time 2. And at time 1, there is not epsilon difference. So in Wasserstein difference, in Wasserstein metric, this model is very close to this one. But the information contained in this model is completely different. Namely, in here, you have to wait until time 1 to realize where you're going, while already in here, young before time 1, you know that if you're going up or down. And it does make a difference in dynamic problems like optimal stopping. It does make a huge difference. And therefore, they introduced this metric, which was in fact in the previous literature, mainly by a paper by LaSalle in continuous time on the path space. But they specialized the tools to the discrete time and deepen the analysis in that context. So basically what we want to say is this definition. First, causality. What is a causal coupling? So I take a joint probability measure between x and x prime, again, x and x prime. Joint probability measure between x and x prime. And now there is time going on. So x itself has 2 steps, x1, x2. It's a stochastic process, the easiest stochastic process. X prime is x prime 1, x prime 2. Causality is, if you think about Monge transport, so transport degenerate with maps, causality says that x prime should be a function of x1 only. X prime 1 should be a function of x1 only. X prime 2 can be a function of both. So bearing the information, carrying the information of x1, x2. Well, of course, for general transport plan, this is the way to write it, which you can summarize by saying that conditional on x1, x prime 1 is independent of x2. Right? So this is causality in one direction. And you may also impose causality in the reverse direction. And then in that case, you call it bicausal or adapted. And you will say, we will say that if bicausal, if also you have causality in the other direction, namely that, well, you just invert x and x prime. So now x1 is a, in terms of Monge transport, x1 is a function of x prime only, x prime 1 only. And then this notation by add is the notation for the couplings between nu and nu prime, which are bicausal couplings. And then we induce a matrix with that. And this metric has a lot of nice features, which I'm summarizing in these slides. Nice features like, well, first, what they realized is that there are various metrics which were introduced in the probabilistic literature. Aldu's metric. There is another metric which was introduced by Helwig, who was dealing with an equilibrium model in economics. And all of these topologies, if you look at how they are defined, they are about looking at the information, so involving condition expectations in the definition of the metric. Anyway, the previous matrix with the adapted Wasserstein distance turns out to be equivalent to all of these matrices in the literature. And this adapted Wasserstein distance, what is shown in their paper is that it induces the coarsest topology that guarantees continuity of optimal stopping problems with continuous bounded reward maps. The typical dynamic optimization problem, if you want. And also utility maximization, if you want, or the typical stochastic control problem, stochastic control optimization here, because it's just one period. Utility function U, increasing concave, any reward, L infinity reward. And again, this usual hedging strategy, the delta hedging, with this notation HO time. I take this opportunity to fix this notation because it's going to come up now in the rest of this talk. So if you use any hedging strategy, zero cost hedging strategy, if there is no interest rate, then this is the return from a zero cost hedging strategy. You decide at time 1 to take this position h of x1 in the underlying asset, and then it costs you h of x1, x1, and the return is, and returns h of x1, x2 over the next period. I think everybody's familiar with this. Buy and hold strategy. And what is proved is that any this map is locally Lipschitz with respect to the adapted Wasserstein for any increasing concave function, any xi in an infinity, and any k because the hedges are bounded by k, so that this works. Anyway, so this is why the reason why this adapted Wasserstein distance has been very popular during the last years. It is more adapted to dynamic problems, and that is the reason why it was the sensitivity result was extended in this paper, which is about dynamics because it's optimal stopping to this context. Okay, so what I want to do is to introduce calibration, so moment conditions, send number of moment conditions to infinity intuitively. I would like to introduce the hedging, or in other words, Martingale restrictions by duality, no arbitrage. Question is, should we use Wasserstein metric or adapted Wasserstein metric? My answer would be no. We should be using the Wasserstein metric in this problem. I will discuss it very shortly. Many of these questions are partially covered by the previous literature, except for the passage to infinite moment constraints. And by doing this, I will be introducing a notion of model risk hedging, which I think might be interesting for practical purposes. Okay. So this was our starting problem. Robust evaluation around the ball. Wasserstein ball for now. No add, no add. Okay, and remember, we can hedge. In finance, we hedge with this zero cost buy and hold strategies. Okay, so you can always add to your position this HO time. If you are interested in risk management, then it's natural to do this. If I add this hedging strategy, the return from this hedging strategy, zero cost, this might lower my risk, and then I would like to add the best one in terms of minimization of risk. Okay, so it's not hedging, it's hedging to minimize the risk somehow. Because hedging, we are used to the hedging in the Black-Scholes theory, which is just kill the risk. The risk becomes zero, right? With the hedging, you just kill the randomness. So in here, it's like in incomplete markets. You cannot kill the randomness, but you can minimize. Is there a best H for minimization of risk? So this is my problem, which I call FM, M like Martingale, big M like Martingale, because of course, everybody's familiar in this room that the duality which corresponds to this is the Martingales. In other words, if I invert the inf and the sup, then the inf inside over h, inf over h, this is a linear function of h, then it's either infinity or zero. And the only way to make it zero is to choose Martingale couplings, right? Everybody's familiar with this. And therefore, there is a similar problem now with f lower bar m, because f lower bar is sup inf. Sup inf is always less than inf sup. So we have that inequality. And f lower bar m is throwing the inf inside, and therefore it's restricting the sup to Martingale models within the ball. I will not answer the question whether these two quantities are equal or not, because my interest is on the sensitivity at zero. But so all over my results would be that these two functions, these two maps, share the same sensitivity at zero. So somehow there is no duality gap at the limit, r equals zero. So these are two concave maps. Both have right and left derivative everywhere. At zero, anyway, it's not defined at the left of zero. And then they agree at zero, and I will show that their derivative also agrees at zero. So my notation for M, these are all measures mu prime, under which the canonical process x1, x2 is a Martingale. Again, because of this inf over h here. Problem number 2. What about adding the add? So the only difference is, I'm just checking that you are familiar with my notation now, because it's getting more and more ugly. I'm just replacing the Wasserstein ball by adapted Wasserstein ball. Okay, and then I put add here. Again, f upper bar, if I minimize the robust evaluation, or I should say distributionally robust evaluation. That's the good name from Operation Research Literature, distribution, DRO, distributionally robust optimization. If the inf is outside, I get f upper bar, but if I write the same problem with sup inf, I get f lower bar, and in that case, because of this linearity here, you are restricting the ball to Martingale models. Problem number 2. I would like to convince that, okay, I will do the two problems, and it will turn out that I will show you that the analysis of this one is much more involved. So the question, while this one is much easier. So the question is, why bothering about doing more difficult things? In the literature, it said that the adapted Wasserstein is better for dynamic models. Why do we insist on Wasserstein? Well, I'm raising the question because there is a debate with Jan in particular and other colleagues. I think it doesn't make sense to do the adaptive Wasserstein. We can do it because it's more simple. And in some cases, maybe the other one is much more difficult to approach. But look at what we're doing here. We have mu, which is our wrong model. And this is precisely why we are computing this robust evaluation and why we are caring about the risk of the model. If this model was good and correct, we just stop there, right? It's a wrong model. And from mu, we say, oh, what about going from mu to mu prime? Okay, and to go from mu to mu prime, we are staying within a ball, right? This ball. So I want mu prime to be close to mu. In the Wasserstein ball, this closeness property is stated in terms of Wasserstein distance. And in the adapted Wasserstein ball, this closeness is stated in terms of the adapted Wasserstein distance. So adapted Wasserstein distance is saying that the transport from this model to this one should be causal in the two directions. So this is a closeness statement. I want to be close to mu with reference to mu itself. But mu is wrong. Why would I want to be causal with respect to my wrong model? If I want to discuss how wrong is my model, I should not take it as a reference at all for this proximity. So I think there is no solid argument why I should be using adapted Wasserstein instead of Wasserstein. Because adaptedness is with reference to the mu itself, but mu is wrong. Why should I look at proximity with respect to this wrong model? Anyway, this is like a philosophical discussion, but I think at the end of the day, we can do both. So let's do both. So M like Martingale, this is with the hedge. M add is Martingale with the adapted Wasserstein. Again, my notations. And there is more. Now I can use calibration to the marginals. I probably don't need to explain this in front of this audience, where the marginals are coming from. In finance, we assume that we observe the prices of vanilla options on each of the dimensions of the X process for any strike, and that is equivalent to observing the corresponding marginal. So there are good reasons why to do that in financial engineering. And now, my problem, which varies more letters, so capital M for Martingale, add for adapted, little m for marginal. What I can do now, yeah, it's getting weird, right?
It's like a Christmas tree.
Yes. So this is my first evaluation, G of mu prime, right? Now I can build so-called semi-static hedging strategies. Marcel is laughing, he knows well this. You have been living with this for a certain number of years. So semi-static hedging strategies. Because I know the marginals, I can buy any payoff F1 of X1 at the price mu1 of F1 because of this calibration thing. I can buy any payoff F2 of X2 at the price mu2 of F2. So that's a zero cost. That's my zero cost. F1 of X1 minus mu1 F1. F2 of X2 minus mu2 F2. Zero cost, right? Another hedging strategy, we have the HO times from before, and now we have this additional static hedge. Of course, this is also has been studied during for many years now in Martingale optimal transport, robust hedging, etc. So this is notation for F1 O plus F2, traditional notation from optimal transport. And again, if you invert the inf and the sup, then you have the same feature as before for the H component, because it's linear in H. It's exactly the same feature as before. So you would be restricting the deviations to Martingale deviations. And for the inf with respect to F1 and F2, this is again linear. And so you have to restrict to those probability measures in the ball which have prescribed first and second margin. Okay, in order for the inf to be not degenerate. How am I doing the time? 5 minutes. Okay, three. Okay. Okay. And one last problem without the add, because I put the add here because this is the one that I will be treating. And without the add, I did not treat it. The reason is that this problem this Martingale problem, this first problem is already quite involved. Okay, so I will be doing 1, 2, and half of 3, and half of 3. Okay, results. 3 minutes for the result. I will be using the derivative of g with respect to the measures. So let's skip this. So whenever you see delta mg, this is the linear derivative, functional derivative with respect to the measure. Okay. Sebastian, remember my notation? M add. Capital M, not small m. That's the capital M.
I can't tell.
Without the colors now. So statement 1, these two functions are differentiable at 0 and share the same derivative, which has the same form as before. LP prime norm of the gradient add projection on the first part of the gradient on the first coordinate, right? There's a condition expectation there. And of the same function, delta mg, as before. Same function. Plus h hat. The reason why I'm writing hat is because this quantity, this norm, minimizes the same norm with respect to any h. So there is a variational problem behind. And you can, in this case, because of this condition expectation, this variational problem is very easy to solve. It's very easy to solve. You just write the first order condition, and the conditioning helps a lot. And so I shouldn't be writing for p prime. Let me write it for p equal 1, for p equal 2. For p equal 2, this is the optimal hedge. Very easy to compute. Think of the linear capital G, then all this is computable Monte Carlo, just Monte Carlo. So this is telling you, this is your first order optimal hedge for model risk. I think this can be useful for practitioners. I need to talk with them about it. And in the recent work by Yan and his student, Xiang, they also have this result. Okay, so let's go. So this is FM add, right? Next, FM. Same statement, except that same statement and same result, except that now it's another H. There's another H. And this other H, as I said, the analysis is quite heavier now because it's really a calculus of variation problem, which is not obvious. And at the end of the day, we can characterize this H bar as the solution of a Fredholm integral equation, which decomposes on 3 functions, psi, phi0, and phi1, with some constants c0 and c1. Phi0 and phi1 are some canonical solutions of this Fredholm equation. Okay, let's skip the details. I don't expect that in this short time you can understand all this notation, but you can see that there is some conditional variance here, and we are dividing for the conditional variance to build the kernel of the Hilbert-Schmidt operator, which serves for the integral equation. So it's a little bit involved, but it's like that. Without adaptedness, it's like that. But again, we have this model risk hedge in quasi-explicit form, if you want. You need to solve this Fredholm equation. Next result. Sebastian, capital M, add M1, this is new, first marginal. That's quite natural, right? First marginal. We still cannot do second marginal. We sort of have a proof in 1 dimension, and we are extending it to many dimensions. And then it will be without 1 and 2, just M. Okay, M1, restricting first marginal. Then you have hedge, the dynamic hedge. Now it becomes H tilde. This was H hat, H bar, now it's H tilde. Actually, in the paper, I'm using the capital M, M1 add also for the H. I didn't want to put them in because other slides would explode. And then there is an F tilde 1 because you can add a vanilla hedge with maturity 1, F tilde 1 of X1. And this is what you find. Again, it's written for general P. I should write for P equal 2. So there is an implicit equation for H tilde. And then once you know H tilde, you can determine F tilde 1 in explicit form. Okay. American option can be done. We're still working on the second marginal. But the main question is it worth it? we have done all this work to drop the add from the problem. Is it worth it? Well, I think it's worth it. We just tried this example, forward start option, x2 minus x1 plus. Here you have the different sensitivities, but what we are really interested in is the blue one is the Martingale adapted Wasserstein, and the red one is the Martingale Wasserstein. You see there is a significant difference. That's the standard deviation. The shadow is the standard deviation. So there's a significant difference. So by going to the adapted Wasserstein, you are losing in conservative if you want. The Wasserstein is much more conservative. This is in relative terms, so dividing by the price itself. You see that for high volatilities, more than 50%, you don't see any difference. But before 50%, below 50%, there is a significant difference between the red and the blue. This is the worst case model because in the proof we can explore what is the worst direction for the first order risk. So basically this transport map. And well, we don't see much in here except that the red is the initial starting measure. In here it's Black-Scholes, I think Black-Scholes, yes. Starting measure Black-Scholes. And in blue is the target measure, is the measure in the direction in which there is the most the worst risk, and you see that it's pushing to the tails. It's Martingale, so it has to be balanced between the two sides of the mean, right? And it's pushing to the tails. So you see that all over the place. And then there are some numerics with American options, same type of observation for American options. In absolute terms and in relative terms. I will stop there. Thank you very much.